brief review of the previous discussion can be like this. Limit as extends to a of integral part of x is integral part of a if a belongs to r minus z, that is non-integral value of a real number. If a is half, integral part of half is 0. If a is 3 by 2, integral part of 3 by 2 is integral part of 1.5, that is 1. Such limits do exist. Integral part of 5 by 2, 5 by 2 means 2.5. Integral part of 2.5 is 2. Therefore, limit as extends to 5 by 2 of that surely exists. Whereas, limit as extends to 3 does not exist. Why? Because for that, left hand limit is 3, whereas right hand limit is 2. Even then, limit as extends to minus 4. Right hand limit is minus 4, left hand limit is minus 5. Even then the limits do not exist. Therefore, as a result or as a summary, we can say that limit as extends to a of integral part of x is equal to integral part of a if a belongs to r minus z, and does not exist at all if a belongs to z. If a belongs to z. Let us see one more example of a limit of a function which differs from both the left hand limit and right hand limit in view of left hand limit and right hand limit. We observe the function f of x is equal to tan x in its domain. Its domain means domain of tan x. We all know that tan x is not defined when x is equal to odd multiples of pi by 2. Odd multiples of pi by 2, that is x not equal to 2n plus 1 into pi by 2. Well, what is saying about limit as extends to pi by 2 of tan x? You may question me. We know that tan x is not defined at pi by 2. Yes, of course. Can we discuss with this or not? Surely. Discussion of a limit is immaterial with the definition of the function at that point where the limit is going to be discussed with. Let us observe the graph of this function. This is y-axis, this is x-axis. Let me call this pi by 2. Let me call this pi by 2. Limit as extends to pi by 2 from left. From left hand side, it goes up, up and up like that. Where can you see that? At infinity, if you can. Therefore, limit as extends to pi by 2 of f of x is pi by infinity. Is infinity. Whereas limit as extends to pi by 2 from left, from right, is You can easily see from the graph itself directly it is minus infinity. So even though we know that tan pi by 2 is not defined, and if you want to symbolize with infinity, it's not possible here. As extends to pi by 2 from left, it goes to plus infinity, and as extends to pi by 2 from right, it goes to minus infinity. Therefore, both the left hand limit and right hand limit do not exist. Sorry, they are not equal here. Hence, we cannot say that limit of f of x, that is limit of tan x as extends to pi by 2, does not exist at all. That is, we cannot say that that limit exists. In a similar fashion, you observe the function f of x equal to 1 by x. As extends to 0 from left, it tends to minus infinity, and as extends to 0 from right, it tends to plus infinity. Even then we say that the limit does not exist. So many people like to say that limit as extends to 0 of 1 by x is plus infinity. I'm sorry to say that it is wrong. You too can agree with that proposal. Why? Because as extends to 0 from right, it is plus infinity, correct? And as extends to 0 from left, it is minus infinity. Therefore, the left hand limit and right hand limit is not becoming equal here. One thing you can believe and say with that belief that that limit does not exist. Why? Because 1 by x purely, if at all there exists in any particular function like that, without any support with the x or any other thing, you can say that the limit does not exist. You see, the problem is, at times we may be asked to have a limit as extends to 0 from left of f of x. Yes, this is only asked. Similarly, if limit of f of x as extends to 0 from right, it only might be asked. What can we say about that? No doubt this limit does not exist. We can believe that, and let us prove it with very simple steps of calculation. I am now finding extends to 0 from left. This is equal to limit as extends to 0 f of 0 minus h. Am I right? As we could believe that left hand limit can also be expressed like this, that is, limit as extends to a from left of f of x is limit as h tends to 0 f of a minus h. We could have already noted. Yes, this is limit as h tends to 0, 1 by 0 minus h plus minus 1 by 0 minus h minus 1 by minus h. This becomes now let me divide both numerator and denominator by e power 1 by h. What is going to happen? E power minus 2 by h you could have noted it, I think. In what way we could arrive this at this step? We could have divided with e power 1 by h, both numerator and denominator. Now it is an interesting case to observe the nature of this part. You see, h tends to 0, h is supposed to be a positive number. In the h concept, h is strictly a positive number. As h tends to 0, 1 by h tends to infinity, e power 1 by h tends to e power infinity, 1 by e power 1 by h tends to 1 by infinity, that is 0. So e power minus 1 by h tends to 0, 1 by e power 1 by h is nothing but e power minus 1 by h, you can say, surely. So it is 0. Use that concept here. 0 plus 1 by 0 minus 1. What can you say? It is minus 1. Like that we calculate left hand limit. Once you catch this concept and the style of making the step, these steps can be observed in your mind itself, and it is not impossible to say the answer on the immediate spot. The left hand limit is -1. Well, let us now calculate the right hand limit. Well, let me cancel these. I think you can believe that e power -1 by h tends to 0 as h tends to 0. Therefore, notice that the left hand limit is -1. Let us look towards the way of finding right hand limit. How can we do that? F of 0 plus h. As we could express the left hand limit like this, we can write right hand limit like that. F of 0 plus h means f of h. So you just replace x by h. What is going to happen? This is nothing but limit as h tends to 0. Come on, e power 1 by h. E power 1 by h plus e power -1 by h by e power 1 by h minus e power -1 by h. As before, as we could do here in this step, let us now repeat the same thing there also. That is, let me divide both numerator and denominator by the number e power 1 by h. Let us see what is going to happen. This is equal to e power 1 by h by e power 1 by h. 1 plus e power -2 by h by. In the previous discussion, while calculating this limit, we could have understood and believed that e power -1 by h tends to 0 as h tends to 0. Therefore, this part e power -2 by h tends to 0, this part also 0, and thereby you will be getting this as 1 plus 0 by 1 minus 0. What is 1 plus 0 by 1 minus 0? 1. But could you notice? Left hand limit is -1, right hand limit is +1. Clearly they are not equal. Therefore, we conclude that this limit of f of x as x tends to 0 does not exist at all, according to our belief or a strong notion. So the limit does not exist. Even though we know that the limit does not exist by looking at the function itself directly on the spot itself, of course, it is necessary for us to know the ways of finding both left hand limit and right hand limit for this function. Yes. To astonish it, if you add just to one x just before this, the limit exists. How? What is that? What is that? If you think 1 by x as an iron leg, you can say x has a golden hand before that. That is, if I write x into this simple x makes a miracle. Previously the limit did not exist, but now the limit exists. What are the changes here? Very simple. Here x extra comes, isn't it? Therefore, in the beginning it is, as you are finding left hand limit, 0 minus h, that is minus h. That is minus h. As h tends to 0, 0 into this part is -1. Therefore, this is 0 into -1 is 0. Is 0. Now, observe the right hand limit also. In the beginning, x is there. So, while calculating right hand limit for x, we generally write 0 plus h or simply h into 0 into again 0 into 0. Please observe the function. Previously, if you have not taken x in the beginning, the limit does not exist. Whereas, if you consider the function with x into, then we say and see that the limit exists and the limit is 0. Yes. Let us observe some more examples. One more most standard example is, consider f of x is equal to sine 1 by x. This is the function. Limit of f of x as x tends to 0 is supposed to be found. This is a famous theorem-like problem in real analysis. It is a famous problem. As it is famous, as it is so famous, so many lecturers and students could remember it at all that it does not exist. Okay, how to make sure or how to agree with that sentence that limit does not exist? With simple numerical calculations, let us see. Left hand limit. Limit as h tends to 0 f of 0 minus h is equal to limit as h tends to 0 sine of 1 by minus h is equal to limit as h tends to 0 sine 1 by h. We know that h tends to 0, 1 by h tends to infinity. What do you say about sine infinity? It is not infinity, but it lies between minus 1 and 1, and nobody knows the accurate value of sine 1 by h. Nobody knows. Some real number between minus 1 and 1 which is not known. Therefore, it does not exist. Left hand limit does not exist. Even if you believe that it exists, what do you say about right hand limit? It is as h tends to 0 sine 1 by h. Even that is not known. Therefore, this is a peculiar case in which both left hand limit and right hand limit do not exist. Yes, therefore, we say that limit of x, f of x, that is limit of sine 1 by x as x tends to 0 does not exist. At this moment also, for this problem also, x, the term x works as a golden hand. This limit exists and is equal to 0. You observe the speciality of the function. We know, we believe, we remember that limit of f of x as, that is limit of sine 1 by x as x tends to 0 does not exist, but limit as x tends to 0, x sine 1 by x is equal to 0. How? Yes, there is a beautiful theoretical support behind that. It can be supported in two different ways. One of the ways, let us now discuss with that. Let there be two functions, say f of x and g of x. Defined in a deleted neighborhood of a real number, say a, such that limit as x tends to a, f of x is equal to 0 and g is bounded. Bounded in that neighborhood in which both f of x and g of x have been defined. Then the product limit as x tends to a, f of x into g of x is equal to 0. You observe here, limit as x tends to a, f of x into g of x Even though limit of g of x as extends to a exists or not, we are just immediately about that. What must we have? G must be bounded. The second function, that is g of x, it must be a bounded function. Let us recollect the knowledge of a bounded function. When can you say that a function is bounded? If there exists a real number k such that modulus of g of x is less than k. Or equivalent to say that if you are able to say that a function g of x lies between minus k and k, lies between this number and that number, this and that, there must exist two real numbers, say k1 and k2, such that all the functional values of f of x should lie between f of k1 and k2. Or equivalently to say that mod f of x is less than or equal to k, mod g of x is less than or equal to k, you must be able to say then g of x is bounded. It must be able to know that there is an upper bound and there is a lower bound for that function. That is, it lies between two real numbers always. The range of that function lies between so and so. If it is possible to say that, with that we say g is bounded, then f of x into g of x is product as extends to a is 0. How far this concept is helpful for us to say? Look here. Limit as extends to 0 of x. How much? 0. Nobody denies. And mod sine 1 by x is always less than or equal to 1, isn't it? The basic nature of sine function, it should lie and die between minus 1 and 1 only. Yes. Its nature. The very range of the sine function is that. So mod sine 1 by x is less than or equal to 1, you see. So is believe, is saying that sine 1 by x is a bounded function. This function tends to 0. This is a bounded function. Let us now make use of this concept. In the place of x, f of x, we have x here. In the place of g of x, we have sine 1 by x here. Therefore, limit as extends to a 0, x sine 1 by x is 0. First part is 0, second part is bounded. Second part is bounded. Therefore, x sine 1 by x is 0. Similarly, can you say that limit as x tan x extends to 0, x tan x is equal to 0? Tan x, is it bounded? Is it bounded? Of course, if the domain of x is restricted to so and so only, between pi by 4 and pi by 3, if you are asked to say like that, in that case, tan x is also bounded. So, that is, if you are able to restrict the domain of x so that tan x is bounded, then you can say it is 0. Otherwise not. There are so many applications for this concept also. You can say that limit as extends to 0, x square sine 1 by x is 0, x cube sine 1 by x is 0, x power n sine 1 by x 0 for all n positive, and limit as extends to 0, x power 4 cos 1 by x is also 0. Like that. There are so many occasions, there are so many applications for this concept. So, the main concept which is under use in dealing with this problem is, if there are two functions f of x and g of x, such that limit of f of x as extends to a 0 and g of x is bounded, then the product f of x into g of x also tend to 0 as extends to a beautiful concept. Like this, we can explain the validity of the result extends to 0 of x sine 1 by x is 0. Yes, there is another important theoretical support for this, namely sandwich theorem or squeeze principle. With two different names it is being called. What is that theorem? Let us see. A very famous and useful result. Actually, it is a theorem. It has a beautiful proof. Theoretical support is there. Let us understand it. First of all, and the way in which it can be used to solve so many typical problems? Yes. Let me try to explain you with a simple demonstration of a humorous example. Observe this diagram. You please believe that this is a building, this is the terrace, there are no steps, but a ladder has been put like this. There are 3 persons. There are 3 persons who like to reach this terrace by means of this ladder. There is a fruit here. There is a fruit here on the terrace of this building. These 3 persons like to have it. First person, second person, third person. After some time, one thing is observed. First person and third person have reached the terrace. What do you say about the middle person? Is he thrown out? No. If he wants to climb up, he pushes him to climb up. The first person and third person have already reached. Means middle person should also reach there. Should also reach there. Isn't it? First person reached here. Third person reached here. What do you say about the middle person? He must reach the terrace to enjoy the fruit. No doubt. Well, what is the reason to explain this scene? I call this L. This is f of x, this is g of x, this is h of x. F of x less than or equal to g of x less than or equal to h of x. F of x less than or equal to g of x less than or equal to h of x. These are 3 real functions which have been defined in a neighborhood of a real number. It is also given that limit as x tends to a of f of x is equal to L is equal to limit as x tends to a of h of x. Both h of x and f of x have reached L. What can you say? G of x must also should reach L. If these 2 things are given in the data itself, then from these 2 we will be able to say that limit as x tends to a of g of x must also be equal to L. If it is possible to have 3 functions f of x and g of x and h of x which have been defined in a neighborhood of a or a deleted neighborhood of a, such that first thing, f of x less than or equal to g of x less than or equal to h of x for all x in the common domain. This is the first condition of data. The second condition of data is limit as x tends to a of f of x, the first one. Limit of x tends to a of h of x, the third one. Both these are approaching the limit L. What is the fate of g? It must also approach L. There is no other go. There has been a beautiful proof also for this, as it is a matter of time, of course, to go through with that, and it is very easy to believe this. So, if at all f of x and g of x and h of x are three different functions, such that f of x less than or equal to g of x less than or equal to h of x, and both f of x and h of x approach the same limit L, then g of x must also approach the limit L. This is what we call sandwich theorem or squeeze theorem, squeeze principle. It is so named because this g of x is placed between two functions f of x and h of x, just like in the case of sandwich. That is why it has been named after like that. Yes. This is what we say about squeeze principle or sandwich theorem. Let us now observe some applications of this sandwich theorem. First of all, previously we were discussing about limit as x tends to 0 of x sine 1 by x. How far it is true with this application or with the theoretical support like this? We shall now observe. That is, we now take interest to show that limit as x tends to 0 x sine 1 by x is equal to 0 using sandwich theorem. How can we support this result? By means of or by making use of sandwich theorem. Look here, we know that minus 1 less than or equal to sine 1 by x less than or equal to 1. Minus 1 less than or equal to sine 1 by x less than or equal to 1. Suppose, let me assume that x is positive. Then what happens? Minus x less than or equal to x sine 1 by x less than or equal to x. Even if x is less than 0, then minus x greater than or equal to x sine 1 by x greater than or equal to x. No problem, it is Unitarian. You see, let me name this f of x, name this g of x, no, h of x, this g of x. What do you say about this? F of x, limit of f of x as x tends to 0 is 0. Limit of h of x as x tends to 0 is 0. So it lies between 0 and 0. The limit of this function lies between 0 and 0. What does it mean? It is also 0. Of course, we are able to have this step by believing that x is positive or by assuming that x is positive. Even if you assume x is less than 0, that is, if you want to find the left hand limit, then also minus x is greater than or equal to x sine 1 by x is greater than or equal to x. Just to reverse the names, f of x and h of x. Nothing happens at all. It makes no difference at all. Hence, limit as x tends to 0 of g of x also 0. That is, the quantity x sine 1 by x is also approaching 0. So like this also we can support the result that limit as x tends to 0, x sine 1 by x is 0. And there are furthermore so many applications are there. Let us observe some of them. Another beautiful application of sandwich theorem we are able to witness. What is the fate of this limit? How can you say about this limit? Or how to guess the answer for this limit? If you ask the same question, 10th class level, he tries to say 1 by n square, root of n square is 1 by infinity 0, 1 by infinity 0, 1 by infinity 0, etc., 1 by infinity 0. He likes to say that it is 0, which is wrong absolutely. First of all, how to identify, how to get the idea of making use of sandwich theorem to solve such questions. This is in the form of a series. You put a small test. You just adjoin n in the numerator of the first term. Find the limit. n in the numerator of the last term, find the limit. If you are able to have both these two limits are equal, then sandwich theorem is to be used. I think you could follow that. You could have followed that. Let me try. You gather the first term here. 1 by root n square plus 1. You join n in the numerator. It becomes this. Tends to n by root of n square into 1 plus 1 by n square. Have brought n square out. What is root n square? N and n will be cancelled. N tends to infinity. 1 by infinity is 0. 1 plus 0 is 1. 1 by root of 1 plus 0 is 1. So, if you join n in the numerator to the first term, you are getting it to be 1. Let us test the same to the last one. You see, all these three steps can be viewed in our mind itself. It might have taken for me some 30 to 40 seconds to put these three simple steps, but it is a matter of 5 seconds to estimate this answer to be 1. Just like that, you do the same for the last term. What is going to happen? N by root of n square plus n. N by root of n square into 1 plus n by n square. Here also it is 1 plus 0 is 1. So, first term and last term, we are going to have the same limit. They yield the same answer 1. Of course, the entire limit is also 1. Of course, this is the easy way of estimating the answer. Yes, within no time, within a matter of 30 seconds or so, we may presume the answer. What is the answer? 1. Okay, how is it 1? How can you believe that it is 1? How can you believe that it is 1? Sandwich theorem helps us. In what way sandwich theorem helps us? We shall now learn. Before going to know that procedure, let me bring to your notice one more question. Limit as n tends to infinity, 1 by n plus 1, plus 1 by n plus 2, plus 1 by n plus 3, plus 1 by n plus n, that is 2n. Can sandwich theorem be used here or not? You can check. Gather the first term, 1 by n plus 1. Put n in the numerator extra. It becomes n by n plus 1. What is the limit of n by n plus 1? 1. You can imagine, you can easily trace the answer. How much? 1. Come to the last place. N by 2n is half. First term, 1. Last term with n gives the answer half. Are they same? Not same. Can you use sandwich theorem here? No. No, we cannot use. Like that, you are supposed to distinguish between the problems. For this one, you can make use of sandwich theorem. For this one, you cannot make use of sandwich theorem. Then in what way should you recollect this answer? There has been another procedure, of course, which we shall discuss with that later, called integration as the limit of a sum. In integration, it has been introduced or involved. By making use of that concept, we shall be getting the answer. And of course, for this purpose, you need not read the entire integration on this part. For this purpose only, there has been very few tips, of course, to have the answer. We shall discuss with them later. And let us now spare time how far sandwich theorem can be used to estimate the answer for this limit as 1. Let us see. To have the answer, you need not put all these steps which I am going to explain you. That gives you a theoretical support or moral support. Yes, this technique is correct. Like this only we are able to have the technique. For such type of understanding only, I like to put all these steps which I am going to have. which I am going to explain you. Look here. Let r be a natural number such that 1 less than or equal to r less than or equal to n. Add n square on all the sides. N square plus 1 less than or equal to n square plus r less than or equal to n square plus n. Take square root symbol on both the sides, on all the sides. Root n square plus 1 less than or equal to root n square plus r less than or equal to root n square plus n. I think you could have grasped the way of obtaining these steps. The first term will be the first denominator, last term will be the last denominator, and the middle term is the general form of all the middle terms. You can see. Now you reciprocate all these things. What is going to happen? 1 by root n square plus 1 greater than or equal to 1 by root n square plus r greater than or equal to 1 by root n square plus n. How could we get this? By reciprocating them. Well, use this step. We now encash this step to have the answer. So for this purpose, I would like to cancel these. Shall I? Taking r is equal to 1. What do you have? 1 by root n square plus n less than or equal to 1 by root n square plus 1 less than or equal to 1 by root n square plus 1. I have just reverted this. I have taken r is equal to 1. Now you take r is equal to 2. 1 by root n square plus n. This does not change. Less than or equal to 1 by root n square plus 2 less than or equal to 1 by root n square plus 1. Now you take r is equal to 3, r is equal to 4, r equal to 5, r equal to 5, like that. Like that. Now you take r is equal to n. What do you have? 1 by root n square plus n less than or equal to 1 by root n square plus n less than or equal to 1 by root n square plus 1. Let me call this entire expression, I like to call this entire expression some Sn. Now, my dear friend, you please add all these things. What is going to happen? 1 by n square plus n, 1 by n square plus n, 1 by n square plus n, etc., etc., like that. 1 by n square plus n. How many times you are adding? N times. So that the sum of all these things is, of course, n by root of n square plus n. What about the fate of the sum? 1 by root n square plus 1, 1 by root n square plus 2, 1 by etc., etc. It becomes Sn is less than or equal to 1 by root n square plus 1. You add all these things. According to the way in which we have constructed these steps, everything is same here. You are adding n times so that you get n by n square plus 1. Here, this is the right spot where we imagine, we think of sandwich theorem. Let me now call this f of x, this g of x, that h of x. If you consider the limit of n by n square root of n square plus n as n tends to infinity, it becomes 1. As we could notice it previously in the beginning itself. You please recollect the technique which we have used in the beginning. First term, take it out. Put n in the numerator. N by root n square plus n. Yes, here it is. Find the limit. What is the limit? 1. Next, take the last term. N by root n square plus n. Find the limit. 1. As the first one and the last one yield the same answer as n tends to infinity, there is 1. Middle number, that is the middle function, should also approach to the same limit 1 by sandwich theorem. Like this, with this as the inspiration only, we could have framed the technique. How are those techniques created with this theoretical support only. If you can understand this procedure, you can never forget the technique of obtaining the limit on the spot itself. It looks so lengthy. Even that, you can say the answer to be 1. Now, let me give you one more example. Let me test ourselves whether we are able to say the answer on the spot or not by looking at one more example. Another example. Can you guess the answer for this? First term is this. You put n in the numerator. What is going to happen? N by root of 2n square plus 1. If you find the limit with our usual procedure, you will be going to get the answer to be 1 by root 2, isn't it? Let us see. The first term with n is n by root 2n square plus 1 tends to n by root of n square into 2 plus 1 by n square. These two can be cancelled. It tends to 1 by infinity is 0. This tends to 1 by root 2. Well, the last one with n by root 2n square plus n tends to n by root n square into 2 plus n by n square is 1 by n square and n square go away. Again it tends to 1 by root. Therefore, the first term with n and the last term with n yield the same answer as n tends to infinity, that is 1 by root 2. Hence, the limit of this function as n tends to infinity is again 1 by root 2. Like that, we can observe as many examples as we see.